All right. Well, good morning, everybody. Welcome to today's webinar. My name's Tony Sandfoss. I'm the technology manager with M4 Knick. Joining me today, I've got a member of our marketing team, Mr. Seth Robinson. Today, we're going to focus on digital technology, smart digital technology. And the topic for today is mastering the digital pH loop. So really excited for the next half hour or so. We're going to go through the benefits of digital technology, do a little bit of a live demonstration. For those of you that are not familiar with our webinar platform, we do utilize Zoom. So please feel free as we go, submit any questions you may have. We'll take about a half hour or so this morning, and then at the end of today's webinar, we'll answer some of those questions. So further, the webinar is being recorded. So a link will be sent out to you at the end of today, so you'll have access to this in the future as well. So with that said, let's go ahead and dive right in and get started. Our goal really for today, like I said, is to explore how digital technology is really benefiting your all's facilities, plants, industrial plants, when it comes to the measurements of liquid analysis. So we're going to review a little bit on digital communication, digital sensing communication. So we'll talk about digital technology and its benefits from sensor to transmitter. And then we're going to spend a little bit of time and talk about digital communication from the transmitter to your control system and how that can benefit end users in predictive maintenance and scheduling PMs and things of that nature. So it's going to be a mix of presentation, talking about digital technology, and then we're going to wrap it up with a live demonstration, show you all some products, and specifically show you all some digital communication coming back to a control system and how that can benefit you. So when we talk about industrial measurements, liquid analysis, specifically pH measurements, we're all familiar with pH measurements. If we're utilizing these in our plants, pH is, one of the top 5 measurements made in an industrial environment. And we use these sensors to both control our process and monitor our process. pH industrial electrodes have been around for nearly 70 years in an industrial environment. And really what's changing, or what has been changing over the last couple of decades really, is this evolution to digital sensing technology. And specifically the digital sensing technology, the communication from the sensing element to the transmitter. So if we look at this diagram here, we see the makeup of a traditional industrial pH electrode. And there are 3 main components to an industrial pH electrode. We have, of course, our pH measuring electrode or membrane. That's typically in the form of a glass sphere or a glass membrane that is sensitive to hydrogen ion activities, which is obviously what we're measuring when we're making a pH measurement. We then, of course, have a reference electrode. Further, we have a temperature detector, and those can all be combined into one bodied pH sensor, or they can be separate. But the job of those 3 components is to develop a potential based off hydrogen ion activity in the process, and then send a signal. Typically, it's a voltage signal from the sensing element to a transmitter, right? And that's what this diagram is representing. Those potentials are all developed and then sent via a voltage signal from the sensing element to our transmitter. And our transmitter's job is obviously to display the pH value. There's equations built into the electronics of the transmitter to take that voltage signal and display it as a pH value. Of course, as its name entails, its job is also to transmit an industrial signal to a higher level control system. Typically, that could be a 4 to 20 milliamp signal. It could be a voltage signal in the range of 0 to 10 volts, things of that nature, to control our process or monitor our process. Maybe that's for regulatory purposes, because we are taking that data and reporting it to an agency to make sure we're in compliance. So again, this is the general makeup of what we refer to as a traditional pH loop. And what we're going to focus on is that signal from the sensing element to the transmitter that you see here in the red box. And when we talk about digital technology, if we see here on the next slide, we're talking about taking those potentials, which are generated by the pH electrode. Still a voltage is being generated based off hydrogen ion activity. And we're talking about digitizing that, taking that analog signal, that small voltage value, and converting it to ones and zeros in the head of the sensor. And the way we do that is through a chip, a microprocessor in the head of the sensor. So as you can see here with this exploded view, the image on the right, the sensor head itself contains a microprocessor inside it. And the number one priority of that microprocessor is to take that analog signal, that voltage, and convert it to a digital signal to allow the ones and zeros to be carried from the sensing element to the transmitter. And most often that's done on standard industrial digital protocols such as RS-485. But the other benefit there is that now that we have a microprocessor, a computer chip in the head of the sensor, we now have data storage. So you can see here, it allows us to automatically recognize the sensor that's connected. Things like the make, the model, the serial number of the sensor are stored in that data on the microprocessor. It allows us to continually look at hours of operation that sensor has been in use. Look at loads, which we'll talk about here in a minute, that the sensor's been exposed to. You know, a pH sensor like the one that I have in my hand may be specified across a wide range. This particular sensor is specified from 0 to 14 pH all the way up to around 285 degrees Fahrenheit. So it can see a very, very wide range of process parameters. Well, when we start monitoring the loads on the sensor, that allows us to understand the health of the sensor itself. And all of that data is stored digitally in that microprocessor in the head of the sensor. And then finally, you know, really one of the most important things when it comes to digital sensing technology is storage of the calibration data. So when we're talking about industrial electrodes, industrial pH electrodes, we all are probably familiar with that those sensors age over time. And we have to compensate for the aging of those sensors, and we do that through the calibration process. Those of you that have a number of pH loops installed in your facility are probably very familiar with this process that's on the screen here, the calibration process. And what I'm showing here is the calibration process specifically with an analog sensor technology. So an analog sensor, again, going back to what we said a few moments ago, is a sensor that is designed to generate potentials based off those three components: the measurement electrode, the reference electrode, and the temperature detector, and it's sending a voltage back to a transmitter. Now, when we calibrate an analog sensor, what we have to do is we have to make those adjustments with the sensor connected up to the transmitter. The reason we have to do that is because an analog sensor does not have data storage in the head of the sensor. The data storage, which is where we're going to store or record those adjustments, is in the electronics of the transmitter itself. So how this typically looks with analog sensing technology is you have to isolate your process, obviously, remove the electrode from the process, from the tank or from the pipe, clean the electrode, and then utilize standards, you know, known pH standards, buffer solutions, to calibrate that sensor. Typically, it's with a neutral buffer solution and then maybe an acidic or an alkaline solution, where we set our sensor 0 point and then we plot our sensor slope. And those values are then stored in the electronics itself. And there's time, of course, associated with that, what you see here on the diagram. You know, maybe it's a half hour to complete that process of isolating, cleaning, calibrating and making adjustments and then reinstalling it. Well, when we look at digital sensing technology, so we go to an analog to digital conversion of the signal, but now we have data storage in the head of the sensor, we can dramatically reduce the amount of time spent in the field. Of course, industrial field environments, oftentimes can be very hot, can oftentimes, have outside ambient conditions. It might be raining or snowing outside, depending on the season and this particular time that you're conducting the calibration of your electrode. Now with digital sensing technology, that can all be brought offline, if you will. These sensing elements can be adjusted or calibrated in the laboratory or in the maintenance shop ahead of time. So you can utilize things like the portable meter that you see here on the screen. This is the Knick Portavo meter. The sensing element can be adjusted with buffer solutions, and that adjustment is now stored, as opposed to in the transmitter technology, it is stored in the microprocessor in the head of the sensor. So your time spent in the field is minimized. So greater uptime of your process. If you have an issue with your pH measurement, you simply take a fresh calibrated sensor out to the point of measurement, put the transmitter into a hold mode, disconnect the cable, reconnect your new sensor that's freshly calibrated, and you're back online with your process. So the number one benefit there is data storage in the sensor head allows for that offline calibration in a controlled environment and at a time that's convenient to the end user, to the operator of the equipment. So digital sensing technology allows for that. If we look at these sensors, which obviously, we have hundreds of these, particularly installed within our plant. If we look at these sensors as true assets, now we can start to manage those assets, because the sensors, of course, have digital recognition in data specifically in the head of them. We can build a database of all of the sensors within our plant through tools like asset management software here. So this particular asset management software, this is the Memo Suite software from Knick, and it allows the Memosens digital sensors to be connected up to this PC-based software to build a database of all the sensors that have ever been connected to it. It allows us to go back and view previous history of the sensors. It allows us to document the calibration process digitally and have digitally kept records of all the calibration. So if you think of this, especially from a corporate standard, you can have multiple facilities utilizing digital sensing technology with this PC-based software, and you can pull a specific sensor up at any point in time, see the history, see the data that it's been exposed to, see the calibration records, generate a calibration report like you see here on the screen at any given time. So digital sensing technology allows us to build up that database of the different assets within our plant and pull records at any point in time because of the digital data of the sensing element itself. So it opens up a whole new realm from an asset management standpoint. You now know how many hours of operation your sensor's been in use, the type of load that sensor's been exposed to, and then further, how much life is left on the sensor. And that's really what we're going to dive into next, is now that we have digital information stored in the head of the sensor, how can we utilize that to get the most out of our electrodes within our facility, to maximize our time when it comes to preventative maintenance and PMs and things of that nature. And that's really where we're seeing this evolution in industrial sensing technology lead to. So what you see here is a standard field transmitter. This is the Knick Stratus Multi here. You see this real intuitive diagram. This diagram represents all the key parameters that we're continuously monitoring on a industrial pH electrode. So you see things like slope and 0 point, which are specific to the calibration of the electrode. You see things like sensor wear and response time. Those are things that we're continuously looking at on the electrode itself. And again, we're storing those parameters, that data in the head of the sensor, and we're plugging them into algorithms that is going into intuitive diagrams like this sensor network diagram to visually give you an indication of what do you need to attend to with the sensor, or do you need to replace the sensor because it has an extreme amount of wear. These diagrams become extremely useful when troubleshooting electrodes. Again, can I clean and calibrate this sensor and put it back into service? Or is it more beneficial because the sensor has a lot of wear to replace it with a new sensor? This diagram would help the end user or the operator understand what they need to do from a troubleshooting and maintenance standpoint. Of course, you also see, operating time, right? So we obviously with the digital sensor are continuously monitoring how many hours and days of operation it's been in use. And then based off that load data that I mentioned earlier, we're calculating how much wear is on the sensor, and further, how many days of life does that sensor have remaining. So intuitive diagnostics built into the field transmitters is something that you gain with digital sensing technology. Now, of course, everything that you see here is available locally at the face of the transmitter, and we'll talk about how that's utilized by operators, but it's also available, folks, digitally via output from the transmitters as well. So if we go to the next slide here, you can see, back to our diagram, our general makeup of a traditional pH loop. That transmitter itself is taking in the signal from the sensing element, right? And for today's purposes, we're talking about a digital signal, ones and zeros generated from the sensor via RS-485 from sensing element into transmitter. That transmitter may or may not have a local display, right? When we talk about digital sensing technology, we can do some really cool things with the transmitter because the transmitter does not need to store as much data. It doesn't need to store the calibration adjustments and things of that nature. So it can be displayless. In fact, it can be just as simple as a 2-wire loop power transmitter built into the sensor cable, in fact. And for those of you familiar with our Memosens product, it's just that. It's a displayless 2-wire 4 to 20 Hz transmitter that's built right into the Memosens digital cable. But of course, the transmitter itself, is transmitting to a higher level controller within our plant, whether that's a PLC or a DCS system that is opening and closing valves or turning on and off different pumps. And if we are utilizing digital communication, such as HART technology or any type of field bus technology, or even Ethernet protocols, which are becoming more and more predominant in industrial environments, like Ethernet IP, Ethernet Industrial Protocol, or Profinet, now we have the ability to not only get our main measurement values, such as pH and temperature from our electrode continuously back at the control system, but we can also have a live look 24/7 at the diagnostics and the health of the electrode via these digital communications. So we're going to spend a little bit of time and talk about that. If you see here on the next slide, this is specific to HART technology, but again, just like all the other protocols that I mentioned, Modbus, Ethernet base, Field Bus, Profibus, these digital communication outputs from transmitter to control system allow access to the diagnostic values that are continuously being monitored on the head of the sensor. So as you can see here, we've got a HART variable selection here in a configuration menu. We're actually going to transition. I'll show a live look here in a second, but you have the ability to not only select pH and temperature, which are your main measurement values that of course we're interested in for controlling and monitoring purposes, but you have the ability to select things like wear percentage and lifetime remaining and calibration timer, so you can schedule PMs based off of that data that's continuously coming back to your control system. So what we're going to do, we're going to switch the camera angle here and do a little screen share. What I have here on my right is our Memorail Modbus transmitter. So it may look a little different compared to what you might be used to from a traditional field pH transmitter that would have an HMI and a display. And that goes back to what I mentioned just a few moments ago. With digital sensing technology, we can do some really unique things on the transmitter side. This DIN rail mounted transmitter is ideal for use in electrical cabinets. It's an extreme amount of space savings. Obviously, it's a little bit less than from a cost standpoint than a full traditional pH transmitter. And the benefit with Modbus communication as an output is now you have access to not only all the digital data, but you can write down to the sensor itself. We can utilize Modbus write registers to conduct a calibration through the Modbus protocol as well. So what you see here on the screen share, I've got a live view. I'm connected to this Modbus DIN rail mounted transmitter. Now I'm bringing it into the framework Pactware, but imagine, if you will, that this is your control system. Or even if you're an integrator or a skid builder, and this is your local HMI where you have all your instrumentation on your skid coming into, we're just simply pulling these Modbus registers continuously. So as you can see here, I have a digital Memosens pH sensor connected to Pactware here. I've got my live values here of my pH measurement, my temperature, my raw voltage. But up top here, you can see these registers. As a standard, we give our end users access to these diagnostic registers. You can continuously monitor them at all times. So you see hours of operation on this particular sensor, just over 1,600 hours of operation. And this sensor is registering just over 9%, 9.6% sensor wear. So how can we begin to utilize that, in our plants? Now, obviously, we can start scheduling PMs based off, say, wear percentage. Now we know, as opposed to sending our technicians or our operators out on a, maybe it's every 2 weeks or a monthly basis to just check those electrodes and clean and calibrate them. Well, why wouldn't we utilize percent wear to give us an insight as to, is it time to clean that sensor and recalibrate that sensor? Or does everything look good? Is our wear percentage minimal to where we can have our technician focus on other things as opposed to sending him out and making their rounds, checking things locally from a transmitter standpoint? So we're going to switch the camera, and we're also going to switch the live view. I also have a heart transmitter connected up. So what you see here on the screen, these are our traditional Strata series field pH transmitters. We've got two versions here. Our Stratus Multi is our standard 4-wire transmitter. So 4-wire meaning externally powered. It is a Class 1 Division 2 rated device. And the 4 to 20 milliamp version comes as a standard with heart protocol. So the benefit there is with heart protocol, and this is not a feature that you need to activate or anything of that nature that you would need to pay extra for. With heart protocol, we have the capability to assign these diagnostic values to our heart variables to bring back to our control system for continuous monitoring. The Stratus Multi also has the capability to communicate via Ethernet IP or Profinet communication. And again, the benefit there with those type of protocols is you have much more data at a much faster rate than even heart digital communication to bring back to your control system. The other transmitter that we have on the screen is our 2-wire loop power Stratus Pro. So this is 4 to 20 milliamp, again, as a standard with heart communication, available with Class 1 Division 1 rating. So you see the nice thing about the Stratus Pro, although it's loop power, so low voltage required to power this device, it has a multicolor backlit display. So from a local diagnostic standpoint, if something were to go wrong, or if this transmitter or loop were to go into a fault mode, you would see this screen turn red. so you can see from a distance. You also see the smiley face, the well-known Senso face. Again, from a high-level, very simplistic diagnostic standpoint, this gives us a visual indication into the health of our electrode that's connected to it. There are three phases to that, right? So if the Senso face is smiling, all is well. It may turn to a neutral face or a flat face. That would indicate that you want to attend to that particular sensor soon. And then, of course, it can turn to a frown face, which means attend to that sensor now. As you can see over here with the Stratus Multi, we can assign the Senso face to a heart variable or to an analog input via Ethernet communication protocol. The way that would look back at your control system, it would come through as either a 0 or a 1 or a 2, which would be tied to, is the Senso face smiling? Is it a neutral face or is it in frown? Very high level, quick indication, but of course, if you're not utilizing a digital protocol, you would need to have somebody view that locally. Further, if they're there locally, they can dive into the diagnostics when using a digital sensor. They can go in to the diagnostics menu. They can scroll over to the monitor function here that you see on the Stratus Pro. And you can view values such as the raw voltage coming from the electrode, the glass impedance coming from the electrode. Of course, as we mentioned, operating time. So we see 96 days. We see 13% wear. Again, if you're just utilizing 4 to 20 milliamp analog signal out of the Stratus Pro, those diagnostics would have to be viewed locally, and they're there always as a standard for the technicians to have an insight. However, if we switch the screen here and you see a live view, again, I'm utilizing Pactware and I'm communicating just via HART protocol here. But imagine I've got a HART input card at my control system. You can see not only am I getting my live pH value, and of course, here's my milliamp signal that I can control with, but I've also got is the tertiary variable and quaternary variable, so our TV and our QV on HART protocol. I've got that percent wear assigned, and I've got days of life remaining also assigned. So now I am continuously bringing those values back over HART. And now, as opposed to sending my operator out to dive into that diagnostics menu at the face of the Stratus Pro, I can begin to start having an insight as to the health of my sensor and scheduling maintenance intervals based off of this data. So it's extremely important when it comes to digital sensing technology to utilize it to its max benefit, right? We can now save time with our operators and have them focus on other things as opposed to doing what we've always done and making the rounds with our pH buffer and our cleaning solution loop by loop to see how are those sensors performing and is it time to clean and calibrate. So this is just HART communication protocol. As I mentioned, you know, from the Knick line of transmitter within our portfolio, we have HART communication, we have Foundation Field Bus, Profibus, Ethernet IP, Profinet. And when using Memosens digital technology, all of this is unlocked and you have the ability to gain much more insight on the health of your electrodes within your plant to get the most out of those assets and extend the life, save you money, both from physical inventory of sensor electrodes, but also from a maintenance standpoint, time and energy of the technicians who are responsible for maintaining these pieces of equipment. So with that, I want to open it up to any questions that you all may have. We'll take the next 5 to 10 minutes or so to answer any questions. Again, just wanted to highlight the value. We talk a lot at M4 Knick about digital sensing technology with Memosens protocol, so digital communication from sensing element to transmitter. But I want to talk about the importance, which we did here today, of digital communication from transmitter to control system and how that really can open things up for you all as end users of this equipment in industrial environment. So I'm going to ask Seth here if we've got any questions which may have come in. Okay, so yeah, go ahead, Seth.
Ryan asks, does it matter what temperature you calibrate the probe?
Okay, yeah. So one question was, is specific around calibration. Does it matter what temperature you calibrate the probe at? And what I would say is yes, temperature definitely plays a part, not only in the measurement of pH, but also in the calibration process. So if you look at the pH buffers that you are utilizing, most often that's a 7 and a 4, or maybe a 7 and a 10. Those buffers are also temperature dependent. So it's very good practice to make sure that you are compensating for the temperature of the buffers that you are utilizing. Now, transmitters and portable meters that have what is called automatic calibration compensate for that. But it is very important that you utilize the temperature compensated value of the buffers when you're carrying out your calibration process. And guys, offline calibration is where that's optimal, right? You can do that in a controlled environment, and you can control that temperature and utilize automatic cal when carrying out your calibration for a more precise and accurate cal. Yeah, so one of the questions that came in is specific to Memosens communication. Customer states, what are some potential issues where we may have a Memosens sensor connected and it's not recognizing the sensor? So let's just highlight a little bit. So Memosens technology in general, we have an inductive connection, so that's very unique. So the sensing element is generating a potential, so there's still an analog signal here that's converted to a digital signal, which is inductively transferred from the sensing element to the cable and then carried on RS-485 back to the transmitter. If you do not have recognition back at the transmitter, it could be simply due to programming or something in that RS-485 chain there that could be causing the issue. When we talk about RS-485, not to get too into the weeds, but on a Memosens cable, you have 4 conductors in a shield. Those 4 conductors, one is for powering the sensor, very low voltage. Memosens is intrinsically safe. So one of those conductors is power for the sensor. The other 2 then are your RS-485 for your communication, both A and B. And then you have a ground wire and a shield. So from a troubleshooting standpoint, to answer that specific question, I would check with your cabling to make sure. It's rare, but of course, one of those leads could potentially cause an issue. But again, the inductive communication is then transferred to RS-485. So it's a standard protocol from that point. And the benefit also is that RS-485 can go much, much longer distances than even traditional analog technology, which you want to ensure is the same voltage coming out of the sensor is going into the transmitter. With RS-485, you can go nearly a mile long without interfering with those ones and zeros. So one of the other questions that we got is specific to the MemoSuite PC-based software. The MemoSuite software is PC-based. Obviously, it can be put on a network. So the calibrations that are stored in that MemoSuite software, they can be accessible if the software is put on a network. Currently, it is not sending that data to the cloud, but of course, you can incorporate other things to send that data to the cloud if you want to access it off the network, if you will. But again, the value is any sensor that's ever been connected up to the MemoSuite software is stored in that database. You can also utilize that software to conduct your calibrations and generate a cal report as well. And then if it's on a network, you can access it obviously from any computer that's on that specific network. So another question that came in was regarding different communication protocols, and specifically, what does M4 Knick and Knick plan to add in the future? So we do have some new industrial digital-based protocols coming in the future. Some of those that are being talked about just in general in the industry are APL-based. If you're not familiar with that, that stands for Advanced Physical Layer. So the benefit there with the advanced physical layer is that now we can get into intrinsically safe environments when we talk about industrial Ethernet protocols. So be on the lookout for that. We will implement new digital protocols in the future from our technology. Currently, we have Modbus serial communication. We of course have HART. We have Ethernet IP, Profinet-based communication. We have a wealth of different digital protocols available from our transmitters, but we will definitely add more as the industry requires it. Cool. It looks like, guys, we just had one last question, and it was specific to today's webinar. Yes, today's webinar has been recorded. It will be sent out. It will also be available in the future on our webpage as well. So again, just want to remind everyone, if you're not connected with us, obviously follow us on LinkedIn. We do have different social media pages, even on Instagram as well. But specifically that middle one, that YouTube channel, we have a lot of how-to videos, short clips, webinars, full webinars like we conducted today, available on our YouTube channel. So a wealth of information there that you can utilize within your plants, spread amongst your technicians to further understand the value of smart digital sensing technology and calibrating offline and digital communication, complete digital loop back to your control system. So check us out there. And then lastly, I do want to do one quick plug. Coming up in a few weeks, I believe it's May 16th, we'll be conducting another webinar that's focused around automation. Our business development manager, Mr. Ron Bridges, he's going to be hosting that webinar, talking about automating the cleaning and calibration process online in the field of these electrodes. So again, the electrodes do age over time, and being exposed to different process characteristics, that aging has to be compensated for via calibration. Automating that, specifically for very important measurements in the field. Maybe it's measurements that are hazardous or not safe for a human to mess with. Ron's going to touch on the benefits of automating that process. So that's coming up on May 16th. Be on the lookout for that sign up. And again, just want to say thank you to everybody that joined today. This has been recorded. We'll send a link out to you all. Hopefully you found value in what digital communication can provide, not only from the sensing element to the transmitter, but from transmitter to control system, to help you with faster uptime and better optimization of your assets, your probes within your plant, but also your maintenance folks, your technicians' time. So hope everybody has a great rest of the week. Take care, and be sure to check us out on LinkedIn, YouTube, and sign up for that automating the measurement webinar. So take care, everybody. Thank you.